As a couple of remarks, if you notice the p-value that we just obtained for running the analysis on the test of independence, the p-value of 0.00104, it turns out to be the same as the p-value that we found for running a hypothesis test on the difference of the two proportions. And this is no surprise because the difference of the two proportions, which has to do with each individual proportion, has to do with the binomial distribution. We call it a binary distribution. And our contingency table here is binomial, or it's called binary because each category has two levels: yes, no, yes, no. The good thing about the test of independence, as I said before, is that this test can be used on any contingency table with any number of rows and any number of columns. It doesn't require the distribution to be binomial. And let's run the test on the actual table right here. Now, some of you may not have a table that consists of multi-categories, so you don't have to do this. But let me copy this table and paste it somewhere else, because this sheet is a little bit crowded. So I copy, I go to sheet 2. Just go down here and click on the tab that says sheet 2 and paste it somewhere. Let's just paste it here. The columns here are a little bit cramped. To fix that, you could manually drag a column to make it wider, or you can select the columns, go to format, and do an auto fit. Format is up here. I say auto fit column width, and that will fix it for us. To run the test of independence on this table, we need to find the expected frequencies or expected counts, and that requires us to find the column sums and the row sums. So let's go down here and label that as column sum. And to find the sum, we use a sum function in Excel. Say equal sum, oops, open parenthesis, and select the column that contains the counts, close parenthesis, hit enter. Apply that function to the remaining cells. We have just found the sum for each column. Let's find the sum for each row. We're going to call this row sum, and apply the function again. Select the row that contains the cells that you are trying to add, and once again drag it down to apply the function to all cells. And if you notice, I dragged it all the way down, and that grand total is basically the sum of these numbers, or the sum of these numbers. Let's find the expected counts. Counts assuming independence. And to obtain the expected counts, you're going to have to do row total times column total divided by the grand total. And we're gonna have to be a little bit careful, just like before. So I again have to introduce that $sign. So type in $sign. That row, the first row sum is sitting in H4, column H, fourth row. So I type in H4 times the row total is sitting in cell D. That's D8. So do D $8 divided by the grand total of 3,453 is sitting in the cell H8, and you need to put the $sign for both. So $H, $8. That is the expected value under the notion of independence for that first cell. And we're just going to apply this to all 4 rows and 4 columns. Drag it down 4 times and drag it over 4 times. And we have all the counts. And you can do a comparison between each observed count and each expected count. And finally, we can find the p-value using the chi-square test. Again, use a function. It's chi-test, open parenthesis. Now, for the first argument or first input, you're going to select a range that contains your sample observations or sample counts. Then you say comma. For the second argument, input expected counts under independence and press enter. And here is the p-value. That p-value is 2.77 or 2.789 times 10 to the negative 5. It's written in scientific notation. I can right click on that. If I don't like the scientific notation, I could right click and say format cells. Right there, you get this window, and click on numbers and increase the decimal points. That will put it in terms of regular notation. P-value of 0.000028 is still pretty small. It's smaller than any standard significant level of 0.05. And the conclusion here is to once again reject the original assumption that the 2 variables are independent. So our conclusion is the same as the conclusion as if you combine this table in a way that you have binary or binomial categories. Now, going back to the original table, let's go back to sheet 1. And let's just focus for a moment on the binary table or the binomial table. There is another way of comparing 2 proportions, and that's by obtaining what's called the relative risk. So let me copy some of my results. I'm going to copy the original table that I have here along with the proportions. So select all those and say copy, go to sheet 2 and paste them. So click on any cell, right click. Here you have many options for paste. You can paste what we have as formulas that we input in Excel. And in this case, we are not going to get the same values that we have. Excel is taking into account the formulas. So click on 1, 2, 3 option, and that will paste the values instead of the values based on the formula. All right, so we have the two proportions. What we can do is to find the relative risk. And the relative risk, if you recall, is a ratio of the two proportions. I would kind of rather take the ratio of the bigger proportion to the smaller proportion. So you say equal, and click on the higher number divided by the smaller number. Enter. That is the relative risk. And what does this relative risk mean? Notice that we have the quotient or the ratio of the two proportions. And in this case, you could interpret this ratio this way. If a randomly selected person from those who say job security is not good is 1.19 times more likely to say that their job interferes with family life than a randomly selected person from those who say job is good. So this is telling you how many times this proportion is greater than this proportion. Let me write that statement down here, and I'll let you think about it a little bit. Give me a sec. Let me try this again. Is actually not good. Is 1.19 times more likely to say than actually a randomly select a person from those who say job security is good. Now, this ratio is unlike the difference of the two proportions. The difference of two proportions doesn't give you a good idea if each proportion is really, really small. So this way you can see that the two ratios are not, or the two proportions are not equally or not equal.